Here's a video from Flat Earth Dave showing the Sun circling the tropics on a North Pole-centered azimuthal equidistant map. In this animation, we can see the characteristic kidney-shaped boundary between day and night shifting as the months pass by. Here, Dave's suggesting that we might be living inside of some kind of glass dome, because from the camera angle he's using, it does look surprisingly similar as the torchlight shines into the paperweight. The question I've got for Dave is, what does he think is defining the shape of the boundary between day and night? So I think with a little help from GeoGebra, we can explore this geometry and we'll get some answers. On the right of this GeoGebra split screen I have the globe, and you can see that I've placed the world map on its surface. Over on the left I have a circle and I've set that radius to 180 to match the number of degrees between the north and south poles. As both surfaces are two-dimensional, all the points that make up the map on the sphere can be projected to the circle, and that includes this point which I can move around wherever I want. Notice the corresponding point on the circle moves along with it. The coordinates of these points aren't exactly the same. On the globe we have latitude and longitude, but on the AE map, one of the coordinates is distance from the North Pole, and the direction coordinate is called azimuth. The distance coordinate is simply 90 minus the latitude, and the azimuth coordinate matches the longitude. So let me enable the trace for the AE point, and I'll move the point on the globe around the equator. And no surprises here, as I trace out a circle on the AE map. But what if I add in a direct line from Sydney to Santiago? Here, the line travels north past Hawaii, cuts through North America and heads south through Mexico before going on to Chile. On the globe, a direct path stays in the southern hemisphere. It's part of a great circle route travelling south of New Zealand, and it skirts Antarctica most of the way. So let's test the projection. I'll drag the point along the globe route and trace the corresponding path on the AE map. And as expected, the trace doesn't follow the direct line at all. Instead we get this huge sweeping curve that travels south of New Zealand. But maybe somebody could argue the opposite. Maybe the globe is just a projection derived from a flat map. So let's reverse the process. This time I'll drag the point along the direct route on the AE map and watch what happens on the globe. And good luck finding a pilot agreeing with a route that has to travel north of LA. So far we've established that every point on the globe can be projected onto the AE map, and every point on the AE map can be projected back onto the globe. And given that real flights between Sydney and Santiago travel south of New Zealand rather than north across the United States, it does seem far more likely that it's the flat map that's being derived from the globe, rather than the other way around. I've updated GeoGebra to give us a globe with an illuminated day side and a darkened night side. To give you an idea of where the sun is overhead, you can follow this subsolar point, and you'll notice I've not confined it to the tropics, meaning I can put the sun directly over the North Pole if I want to, which lights up the northern hemisphere, or over the South Pole, lighting up the southern hemisphere. The point is, no matter where the sun is, 50% of the Earth is experiencing day, and the other 50% is experiencing night. So how do you go about placing all the points that make up day and night onto the AE map? Well, it involves a bit of trigonometry which I won't go into right now. You can hit pause if you want to read all the steps I took, but basically, every point on the terminator line is exactly 90 degrees from the subsolar point, and by knowing this, we can arrive at a formula that will calculate the latitude of every point that makes up the boundary. Here's that formula put to use, and I've combined it with another formula that estimates the sun's declination, so I can get this cool animation as the year progresses. And it's important to understand exactly what we're looking at here. Make no mistake, this is the globe's day and night geometry projected onto the AE map. The yellow region represents half the Earth experiencing day, while the shaded region is the half experiencing night. And I know what some of you are probably thinking. You're thinking that there's no way those regions are always equal, but you mustn't lose sight of the fact that the areas on an AE map become increasingly spread out the farther south they are. A single square mile in the far south will take up vastly more space than a square mile in the north. For example, on a sphere, the area covered by the polar regions would be the same, but here, the southern polar region appears roughly 14 times larger. Distortion is just unavoidable when you're projecting the spherical Earth onto a flat plane. Let's look at it another way. If I move the subsolar point to the outer edge of the circle, then the Sun is effectively over the South Pole, and all the northern latitudes fall into darkness. This darkened area is clearly not 50% of the AE map, but it is 50% of the globe. And if I take the subsolar point to the centre, the situation reverses and now it's all the southern latitudes turn to be without light. Again, that's 50% of the globe, but it does look considerably more on the AE map. The Time and Date website has the real-world position of the Terminator in real time, and here we're looking at the 27th of January, 8:16 UTC. Notice the subsolar point is just off the coast of Madagascar, and I've picked out some notable places that are on or near the Terminator line. It doesn't quite reach Antarctica, but you can see that it travels just east of the Falklands. It brushes the coast of Brazil. We keep going north toward Edinburgh. We can see that it cuts through Japan just west of Tokyo. And then we can follow it south all the way to Queenstown, New Zealand. Now let's see if I can reproduce this on the AE map in GeoGebra. The subsolar point looks good, and we start off down here, just north of Antarctica. Here's the Falkland Islands. The coast of Brazil checks out. Edinburgh, yep. Japan. And finally, somewhere near Queenstown or Dunedin on New Zealand's South Island. So I'd say that's an extremely close match, and we shouldn't forget where this shape comes from. At first glance, the geometry can seem quite complicated, but once we break it down, the underlying mechanism is actually very simple. In Flat Earth Dave's demonstration, the effect only appears when light is refracted through a curved glass paperweight, while the torch is moved in and out at specific angles. And it's important to point out, the appearance will change depending on where the camera is positioned. The geometry we've explored doesn't rely on viewing angle tricks or optical distortions. The Terminator line emerges naturally from a rotating ball in space, orbiting a distant sun. So let's bring back the 3D globe one last time, and I'll set the sun's position to the 27th of January, just so that we can check out what's being projected. Again, the subsolar point is near Madagascar, and following the Terminator line we have the Falklands, the coastline of Brazil, Scotland, Japan, and New Zealand. But there's one final consequence of this geometry that's especially important, and I'm referring to the 24-hour or midnight sun in Antarctica. If the AE map is indeed just a globe projection, then we should see Union Glacier, that's this point on the outer edge of the circle, experience 24 hours of continuous day in December, something many flat earthers prior to the final experiment said was impossible. So let's get the sun circling and see what happens. We'll start off in March and we'll see that Union Glacier is getting roughly 12 hours of day and 12 hours of night. In June, well, the sun never rises there at all. September, again, roughly 12 hours of each. But now watch what happens in December. And surprise, surprise, the sun never sets. How did Dave miss that? So I think on that note, I will leave this video here. You'll find all 4 GeoGebra links in the description, so do have a play with those. Please like and share if you can. And yeah, thanks very much for watching, and I'll catch you later.